Okay. Okay, so what I'm going to do here is present what I'm calling the GroundTruth method. It's one of our contracting companies that actually designed, and we worked together to design this new techniques. So the reality is it's pretty well. I gave this talk at one of our at the MDRU UBC there a couple of weeks ago, and it's part of this talk. But it's about new technology, and that was driven by we call it the modern day gold rush. And what we have here is Isaac Fage here working on the drone. We have Chad. These are the team members. Cote, he's working on this new DC resistivity. Teo Henderson is the guy who built basically the hydraulic type guy wizard. So he built this GT probe that I'll show you in a few minutes. And then he also built this RAB, and we have Dan there running it. So what we actually do is have a team that's dedicated and to basically coming up with new solutions. And the idea is that we're following this guy in the middle, like we're about 100 years behind him. So it all started with this soil sampling, and that's the big thing here is everybody forgot that the key critical start of this, of any exploration, is taking high quality soils. So we started developing this technique in 2002. And the idea was that we could follow up in this non-glaciated terrain. If we went deeper down with these soil augers, we could actually get better gold results at depth. And then it become a numbers game. And the idea was we just gather as many soils as possible, and stack them up like cordwood, and then map out these mineralized systems. So we put a lot of effort and emphasis on training programs, and that's what we started with. We actually put together like literally high quality like training programs. We actually train young people pretty well like a military training program. And that was the idea. We'd have a 2 to 3 week training program, all to take high quality, I call it scientific data, which was a soil. So here we see, and the reason is because it's very expensive to actually work up there in a sense if you're disorganized. So the idea is that we could actually organize crews and basically get out in the field and take these good quality soils. And this is kind of just a rundown of how we started to work. We run with these ridges and spurs, and the idea is you could just see this little hit. Now this is if we're running on a ridge top, taking soils on 50-meter spacings. And if we get a couple of hit wonders, as we call them, then we follow it up with, this was a big grid program that we came in behind it. But you could actually see the results that fell behind those two soils that we nailed here. And this was actually part of the coffee system. But you could actually see the results, like how much gold there was lying next to these two guys that didn't look like too much. So that's the idea, is that that's our follow-up system. But the problem becomes, like such as the coffee here, this is the 2009 work, I call lots of smoke. Where's the fire in these big smoky areas? So this is over 2 kilometers by about 3. And this is the Supremo, the Latte, and the Double-Double. So that's the Kaminak's main gold bearing, like that's where their pits are going to be. So we had to come up with a technique to follow these things up. Like our traditional techniques were using big backhoes, if you could get them into the area. And then we actually brought in these small little backhoes, and we call that the serendipity in science. But the reality is we realized that we only needed to actually excavate shallow trenches and sample them on representative samples to actually across down the trench. And that produced some good results. And I call this the can-dig era, because a whole pile of these things got sold and sent to the bush to start following up on the soil anomalies. But it was still quite slow. So, and then the idea was you had to come back and backfill the trenches. So it was working, and it was better than, I say, 6 guys and shovels. But the idea is we had to come up with a better solution. So here it led to the discovery, as I said. Here's the discovery holes of the white, on the white golden saddle, me and Isaac, the owner of GroundTruth, or the president. And then here we are, me and Isaac are visiting the trenches that we did on the coffee, on the T3. That's the discovery areas. So the idea was it was working. But when the downturn came, we said, we got to figure out a better way here. Like, it's working, but can we come up with a better way? So the idea was, can we find a cost-effective, environmentally friendly way to explore the Klondike? Just like this guy up here in the corner was doing back about 100 years ago, scratching his head going, crap, I blew my budget. Can we figure out a better way here? How do we do this? And so that's what we ended up doing for the last 2 years. So the next part we call drones to drills, and the idea is that we just ask questions. Okay, we need good data from the topo DEM. Pretty well like a military thing, we need good recon data. So the idea is we looked at a bunch of drones, but we ended up picking this drone up here. It's called an EB. And that thing, we could hand launch it from a helicopter pad from the middle of nowhere. It goes and does its mission and comes back. And the idea is that we could get an ortho photo, we could get a DEM, and you could see how you could actually even play a little bit with the DEM. And you know, this is actually a snowbank right here in this corner. And this is, we started looking at it, like this was the first 2 days of our projects, or getting this drone, so we were just experimenting. But here, this is our backyard of our office area, and you can see these skidoo tracks. And you actually see how these skidoo tracks are showing up so well. So now we knew we could actually use this tool also to map out structural lineaments. So it was kind of a, it is a groundbreaking little tool here that we're allowed to use. So this is some ortho images taken from the drone. Then we could create these elevation models, and then we could actually produce these contour, like really detailed contour, basically topo maps for our background. So it has a lot of applications. So that's how we use it. It's kind of the 3D blueprint of our work site. And this is how it's working. It's air photogrammetry on steroids, as I call it. And to give you an idea, this is one 3 centimeter or 4 centimeter point, data point, a pixel. And it's triangulated by about 30 to 40 images. And so this is where the photos were taken. And that's how we're producing these things. It's like, this is like technology that was 20, 30 years ago, except that it's pushed faster, and it's, instead of having 2 ortho photos, we have 30 to 40, so you get a better resolution on the topo and the DEM, like elevation. So that's where this is all moved. But this is because of modern science, again. This is another thing it's done. We could actually go down to ground level and have a look to see what the terrain looks like, even at ground level. So this is a placer miner that strips some ground. And you can see all the pixels, and that's what they are, data points. But you can see this tree sitting up here, and you know, this is probably about 8 centimeter resolution. So these pixels, so we could fill these in if we wanted, but this is just showing you how the data. So it's the closest thing that I call it the Star Trek that says, beam me down, Scotty. And you could look at ground level to see what's kind of going on. The other applications we use it, when we fly a site, we could actually tell what the previous work was, and here now I could actually count the 2x6s on the drill pads to see if we have enough with these 2 drill pads to make 1 drill pad. So that's the kind of stuff that we're using it for. It's got a lot of applications. Here's the cool thing that we really like. We actually realized we could create these really cool 3D DEMs or ortho photos. But the idea is then we could overlay all of our data on this. So it becomes a quite practical tool for basically seeing how you're working. So once we did that, now we got the high-res topo DEM, we got that reconnaissance data. The next thing was we had to come up with a different way of actually figuring out how to find the smoke and the fire with all this big soil anomalies. Can we come up with a tool that we could run across the ground and give us an imagery of an idea what's going on underneath? So that's what we ended up doing, was we started working with this 3D, like it's a DC resistivity, and it was from the environment world. And the hard rock world is used to, they actually understand IP, and this is what it is, except it's low-powered system. And what we ended up doing was, instead of putting 25 or 50 meter electrode spacings, like they do in normal IP surveys, we ended up doing, these are 5 meter electrode spaces. So it's super high resolution imagery. And the idea was, or the thought was, that if you have a soil anomaly that's daylighting, it must be 90% of the gold targets out there in the world are structurally controlled. So the idea is that we should be able to map out the structure and actually see it. So that's what this is what the hypothesis was when we brought this tool in a couple of years ago. And here we just walked across the latte, and you could see how we hit the target right away. And here's their drill sections. So this was a new breakthrough tool that we really liked. We started working with it quite a bit before we brought it out into the public. But again, here's all that smoke, as I say. Here's a big soil anomaly on the coffee project. So we ran some test lines across, and this is where the latte was I just showed you. And then we ran some, this will be the T3, T4 area that I'll show you in the next one. So here it is here. So here you see the big smoky green outer edges of the soil anomaly with the hot red ones in the middle. But this is the structures that you can see. There's the T3, there's actually T4 here, and then there's T5. So we ran a line across here. Can we see something like this that normally you don't see with the normal IP surveys, these multiple structures that are lighting up, these big soil anomalies? So we went in, and sure enough, there was our first pass here. Here it is here. That's permafrost on top. We could start seeing, but we see these resistivity low areas. So there's the T3. Here's the T4 area, and here's the T5. So again, now here's the IP effect. Now that's telling us because it's oxide, it does have a chargeability high associated with it. And there it is. There's the T3, here's the T4, and here's the T5. It's not a bang-on science, but it's pretty close. And the idea was, it's the prep work that we're going to use instead of trenching. We use this GT probe. And the idea is that we're looking where the resistivity low is daylighting out. And it gives us vectoring tools to go and test the GT probe. Here we tried it on the QV property, on the BG zone. And here we had some nice trenches coming across here, lighten up. So we ran the survey, and you could actually see the resistivity low following the mineralized structure where it daylights. So the idea is that, okay, this looks like it's starting to work. Now, like statistically, if I didn't have the drill hole data, I probably would have tested over here in this area also, just if we had gold up in there too. So here it is. Here's actually a long section. And the idea is that this is the ore zone up here in red. That's where it's daylighting. So we actually paralleled the ore zone to see if we could see what we could see. Because normally you do cross sections like I showed you earlier, the previous slide. So here's the long section. You can see where this is the trench daylighted here. They drilled into here. And you see the resistivity low. And you see this nice drill hole intersection. But you could actually see where the ore actually is plunging down. And then flattens out. And then gets hit with the next drill hole. So we actually have now a new way of looking at the mineralized zones that are basically daylighting. So it gives us an idea. Now we're only looking about 100 meters up and down. Here's the Plaza project. And the idea was this is a granite body, and there's a structure that daylights, and it turns out to be it's a resistivity low, which most of our structures are. That's what it is, because there's a little bit of water and it's all broken up. But here the Plaza actually had sulfides with it too. So you could see how it's lighting up with the chargeability high. So this was like okay, now we have a new way of actually looking at these things. And then what we ended up doing was we actually approached the government, the Yukon Geological Survey, and the feds, and proposed a big research project. And we ran a whole pile of different case studies across different properties, various properties across the Yukon, about 9 of them. And we actually put them out in actually a public publication that people could look at, because I think this is a new tool that was overlooked, but because of modern technology has allowed us to put like 84 electrodes back to back 5 meters. This will be kind of a new tool in our toolbox to use, especially for these mineralized zones at daylight close to surface. So once we found these structures at daylight, the next thing was to figure out, can we come up with a better tool than the hole to find them? And so this is what we ended up putting together. This is a hammer drill off the shelf. It's called the GeoProbe. But we put them on a special set of lightweight rubber tracks that are hydrostatic drive and that could just motor through the bush like there's no tomorrow. So it's 2 helicopter picks. We drop it in, and this thing will even work on 45-degree slopes. So the idea is that what we do is we pound a hole down 6 feet. We go down to the bedrock interface, but our old historical trenching went down 4 feet, 3 to 4 feet. So we're going down 6 and a little bit deeper. So the idea is this thing moves around, punches holes down, and then what we actually do is XRF it. But the beauty is it's run remote control, so the safety issue is taken care of. But it wiggles its way through, and it actually hardly leaves a footprint behind it. And so here you can see it snaking through the bush, following the guy. And here we are moving it up a steeper hole, or steeper slope there. And the idea is then there's a helicopter booting in the background working with us. And this thing could evaluate ground. It actually does 3 times more ground than the hoe. The hoe used to do 75 meters a day. This thing does about between 200 and 250 meters a day, depending on the ground conditions, with no reclamation costs. If there's nothing there, you don't return. But what we actually do is we work with an XRF with it, and we actually get live data. So here's some trenches on the QV project, and that's where the anomalous can dig trenches are. And here we ran a case study in between running the GT probe, taking 5-meter samples. And that's what we do now. We actually sample it on 5-meter spacings. And that gives us good resolution, and it hits the target. As you see, it hit it nicely. We tried different fraction sizes. This is a 2-inch sampler, and this is a 3-inch. So we went with the 3-inch because we had better rock samples coming up, bigger sample, and the geos really liked it. So we've modified it quite a bit there. But this is where we run with this portable XRF on site. As we're pounding holes down, the samples come up, and we analyze the rocks and the soils. And here you can see now, normally this is gold here, and this is arsenic, antimony, moly, iron, barite, and mercury. Normally we get pathfinder elements with the gold. So if we didn't see the gold, that's okay, because this XRF is only really good for 10 grams plus. But we would know we're in the mineralized zone by the arsenic, antimony, and moly. Now, like most gold type deposits have different signatures. So what we actually do is map out. Sometimes it's only moly, sometimes it's only arsenic, sometimes it's a combination. So we actually figure that out before we go in the field or while we're there, and then we know what we're seeing. So here you could start to see zones. So the idea is that we take this data every night. It's basically broadcasted. We put it out through satellite link up in the field camps, and we send that to the base camp in Dawson, and then they make these histograms, and we get this to the geo. So the idea is that, like, this was a job that we're doing. There's one guy who was coming down here. That was one day's work. Before we moved the GT probe anywhere, the geo was able to say, can you guys just go and hit this section over here so that we could detail this step out about 100 meters. And the idea is that we still send the bottom of the hole rocks for true assays, but we're getting live kind of data, and we're able to make decisions in the field right now. So this is, again, another breakthrough. And it's kind of the same thing with our DC resistivity. All them inversions that I showed you previously, we actually do them at night, and so that we could actually make decisions the next day. So everything is, this is the whole new way of doing things. It's like fast, and it's making decisions on the fly while we're in the field. So once we actually nail that zone, and we know, okay, that's a hot zone and it daylights up, and we pinned it down to plus or minus 5 meters, the next question everybody has is, how deep does it go? Okay, traditional sampling, diamond drill programs, we're running $500 plus a meter, $500 to $600. So we had to scratch our heads because that's where a lot of the money gets dumped and burned in that part of the exploration program. So we scratched our heads once we had the GT probe figured out, and we said, can't we put a rotary air blast drill, which is like an RC, but it's an open hole, on the same track platform that we have the GT probe working on, to basically go and test out the depths, like deeper down. So we actually built one prototype about 1.5 years ago, and the irony was we scrapped it, and we said, okay, because it didn't quite work well. Went back to the drawing board. That was last May, the end of last May, we went back to the drawing board and actually got a prototype up and running by the end of July. And this is kind of the prototype one. But it's now we've modernized it quite a bit. But this one actually has an onboard compressor. And this thing has the capability on its own to drill 50-meter holes. And the idea is that this thing is working on air. So this has got an onboard compressor. But if we plug in the bigger compressor, we could actually get 100 meters in a 10-hour shift or 12-hour shift for 20 to 25 cents and $1 compared to the diamond drill cost. So that's where we changed it up here. And the cool part about this is we don't actually even need a permit to run this thing because it's so non-evasive. It's under 5 feet wide, doesn't use water. So now we're hitting all these kind of cool hits as from the environmental point of view and from the permitting point of view. So the idea is now we have the tools to go in and recon this area. And these are the chip trays that we produce. And so the guys log them, they zap them, and then they put little chips for the geos so that they could actually map out the mineralized zones. So now you could see it. Now these are all 5-foot sections. So you could kind of see what's kind of going on. You're not rock and it's not core, but it's good enough, and it leads you into well, you're able to now make a good choice of where you want to diamond drill. The big thing with rotary air blast drills is that they're open hole. And so people were worried about cross-contamination. So here we went through a very high-grade section of 5 feet of 20 grams. And what we noticed is that the tail behind it is very minimal. Like these are 5-foot sections. And so what happened here is we know the tail was, if there's no gold in this next 5-foot section, after we drilled the 20 grams through 5 feet, there was a 0.5 grams and then a 0.3 grams on the next 5 foot and then nothing. So that, we call that a 10-foot tail. There was no significant, we know what it is, and we know that this is a very good, this averaged 12 meters of 5 grams. We know if we come back with diamond drills, we're going to kick butt in here. So this is the idea. This is 20 cents and $1 again. Here's again another log hole. Same thing. We could actually see there's a good hit, and that might be a tail right here. There we have multiple hits, and we see again a little bit of a tail, a 5-foot tail we call it. Again, 5 to 10 feet. So no big deal. And the idea is that, you know, this is not 43-1 basically resource grade drilling, but it's 20 cents and $1 drilling that allows us to have, you know, 5 arrows instead of 1 arrow when you go hunting. And that's the whole trick to this game, increasing your probability odds. So that's kind of the techniques that we put together. And what that really has led us to do is, this is the dramatic difference, is what normally would cost us 2 field seasons in the Yukon, because you're only working in the summer months, be about $500,000 to $750,000 over them 2 field seasons. We actually conduct that same work program in 2 weeks. We could do it any time of the year, but we like it better when it's not 40 degrees below zero. But the idea is we could do it any time of the year in 2 weeks for around $100,000. So we've actually dropped our basically exploration costs down to 20 to 22% of what it was 3 years ago. And the big thing is we could gather the data any time of the year. So if you needed some trenching data tomorrow, I would have to tell you have to wait till the end of June before the ground thaws out good enough. And now we could go out tomorrow and get that data to you by tomorrow night. And so that's the whole trick of this new business, is we could gather the data fast and high quality and cost efficient.